Today we're going to talk about Lesson 531, Patterns of Growth in Sequences. I'm going to give you three sequences, A, B, and C. The first thing we want to do is we want to know how does each sequence grow. So if we look at sequence A, we see that they're increasing by 1, so we look at the T of n column and we say, all right, what's the difference between 54 and 27? Well, on your calculator, you'll see that if you add 27 to 27, you'll get 54. And 54 to 81 is also 27. And the difference between 108 and 81 is also 27. So it looks like that this sequence is growing by a constant of 27. So we can say the sequence generator of sequence A is positive 27. All right, looking at sequence B, you find the difference between 9 and 36 is also 27. The difference between 81 and 36, though, is 45. And if you add or subtract 144 and 81, you get 63. So I am not adding by a constant here. And if I tried to multiply, if I multiply 9 times 4, I get 36. But the only way I could multiply 36 and get 81 is I have to multiply 36 by 2.25. And so it is not multiplying by a constant, it is not adding by a constant. So therefore, I would say there is no constant adding or multiplication. My third sequence, if I look right here, I'm going from 6 to 12 and from 12 to 24. If I multiplied 6 times 2, I would get 12, and 12 times 2 would give me 24, and 24 times 2 would give me 48. So my sequence generator in sequence C is multiplying by 2. Number 2, it says, which family of functions best models each sequence? Well, since I am adding the same thing every time in sequence A, what type of sequence would that be? Well, it's in the family of linear sequences. This one, sequence B, there is no constant growth. So it is not linear and it is not exponential. So we would say that this is other. And for your information, this is actually a quadratic sequence. Sequence C, which family of functions does that one fall in? Since I am multiplying by a constant of 2, this must be exponential. Okay, number 3 says, can you write an equation for any of the sequences? Well, on sequence A, it's linear, so I am going to find my M and my B. Well, my slope is 27 because I'm adding 27 each time. My starting point, however, I can't see yet. So I'm going to go up here and I'm going to go back to 0. And if I'm adding 27 going down, I'm going to subtract 27 going backwards. So 27 minus 27 is also 0. So my B is 0. Since this is a linear equation, I found M and B, I can write its equation. Its equation would be, and again, since this is a sequence, I'm going to say T of n is equal to mn plus b. Well, m is 27 times n plus b, but b is 0, so I don't have to write it at all. And that is my equation, my linear equation for sequence A. Now, I am not going to write an equation for sequence B. I know it's quadratic, but we don't know enough about this yet to write the equation, so we're not going to worry about it right now. Sequence C. Well, since it's an exponential function, we are going to find, instead of slope and y-intercept, we are going to find the starting value and the multiplier. The starting value I can't see, so it's kind of like I am finding b. I'm going to go backwards to 0. Since I am multiplying going this way, I'm going to divide going backwards. So 6 divided by 2 is 3. So my starting value is 3. My multiplier, I can see right here, I am multiplying by 2 each time. So that is my multiplier. Okay, now this is an exponential equation. So I'm going to say t of n equals my starting value, which is 3. And what do I do? Each time I am multiplying by 2, and I am raising that to the nth power. Okay, number 4. Suppose each sequence represents a savings account. N is the number of years, and T of n is the amount of money in the savings account. I am going to graph the 3 sequences on the same graph from 1 to 4 years only on the back of this note sheet. I'm going to use pencil for sequence A, I'm going to use red pen for sequence B, and I'm going to use blue or black ink for sequence C. There may be some colored pencils there that you can use, but try to use a different color for each one so it's obvious which points go with which. And even though these are sequences, we're going to connect the points with dashed lines to see the growth better. So normally we would not connect the points with lines because these are discrete, but for today we're going to go ahead and connect them with dashed lines just so we can see everything better. And what we want to know in the end when we look at our graph is which account would we want to have our money in after 4 years. Moving on. Okay, if you turn your sheet over, you will see this. We have the first 4 years for each sequence here again, and you'll notice that I've marked in color, I have put which color I am using for. I'm using pencil for A, I'm using red pen for B, and I'm using black for C. So you might mark that on yours so it's very clear. I also put my starting values in. And I am going to put in here because that's where my X would be. And what does N represent? They said on the other page that N was the number of years. That's our time. And then the column where we normally have Y would be T of N. And what is that? That was how much money we have in the account. So that would be the amount of money in the account. So that's how you would label your axes. And now you are ready to graph. So what I would like you to do is pause this recording and I want you to graph those 3 sequences. Now I highly recommend that you start with sequence A using pencil and you plot those points and you do your dashed line and then you label it sequence A at the end of that line at 4 years. And then do sequence B, plot your points and then do the dashed line before you go on to C. So it's very clear that which points go with which sequence. So pause the video now and graph those 3 sequences all on the same graph. Okay, I'm about to turn the page. Here we have the results of graphing the first 4 years of our bank accounts. You'll notice that 2 of them start at 0, 0, and sequence C starts at 0, 3. So it kind of looks like there's $3 in sequence C. So as you look, as the years pass, you'll notice that sequence A is the highest line it has the most money in it up until year 3. If you look at year 3 right here, you'll see that that's when sequence B catches up to it. You'll notice that sequence B is second place. It has the second most money until year 3, and sequence C has the lowest amount of money the whole time from years 0 to 4. Okay, so what account would you like to have at year 4? Which account would you want your money to be in? Well, obviously, since sequence B is the highest amount at 144, we would want our money there. Make sure that you have everything labeled and make sure that your graphs are correct. Okay, now what I would like you to do is you'll notice that the sequences actually go to 7 years on the back of your sheet. So I want you to complete the tables on the back of the sheet to 7 years. And I want you to graph the additional points on the same graph that we just worked on. We want to know which account will have the most money after 7 years. So let's look at those charts and let's fill those in if we can. If you look at sequence A, I went ahead and I put the starting points up there. And remember, we're increasing by 27 each time. So you're going to continue to increase by 27 and you're going to fill in the rest of the table. So when you do that, 128 plus 27, that is 135. Plus 27 again, which is 162. Plus 27 again, which is 189. Sequence B, you'll notice that I've already filled it in for you because that's the quadratic and there is a way to figure it out, but we haven't talked about it yet, so I'm just giving it to you. And then in sequence C, what did we do before? We multiplied by 2 each time. So I'm multiplying by 2 each year. So 48 times 2 is 96. 96 times 2 is 192. And 192 times 2 is 384. So once you have your charts filled in, you are going to graph the years 5 through 7 on your graph. Now, maybe not all of the points will fit, so just put as many points as you can. You're going to still use the same colors, and you're going to do the dashed line so you can kind of see what's happening. So please pause the video and complete the graph. And we want to see which account would be the best one for us at the end of 7 years. Okay, I'm going to turn the page. Here are the final results. You'll notice that here's what our graph looked like before, right here at year 4. Okay, sequence B was ahead. So what happened after year 4? Well, you'll notice that sequence B is still in the lead. It's still the highest one. And notice sequence A. Sequence A was the highest until year 3, and then it was middle of the road. And then between years 5 and 6, right here, sequence A became last place. So it was first at the beginning, it was second in the middle, and it's last at the end. You look at sequence B. It started out second place at the between years 0 and 3. It caught up to sequence A, and then it was the highest one until it went off the graph. Sequence C started out and it was in last place all the way until between 5 and 6 years. And then at 5 and 6 years, it's still in second place. But as it's going up, you're going to notice that sequence C, this black dash line, it's getting really close to the red one. Now, we don't know what happens exactly based on the graph, but if you look down here at your charts, at year 7, third place is sequence A, first place is still sequence B, and sequence C is in second place. But look how steep the black line is. It's actually becoming steeper than the red line. So if we did year 8, and we add 27 here, we get 216. Here, I will just tell you that the next amount in this graph is 576. But in year 8, if I double it, I have $768. So which one of these, after year 7, would we rather have our money in? Looks like sequence C would be the best. If we were going to do a long-term savings account, we would want to put our money in something, that account that ran like sequence C. If you only had your money from 1 to 3 years right here, then you would want to keep your money in sequence A, because if you're going to do short term, that's going to give you the most money. From 3 years until, 6 years, from 3 years until 7 years, because this is still in the lead right here. From 3 to 7 years, if you were going to keep your money in your savings account for 3 to 7 years, you would want to put it in an account like sequence B. However, if you were going to keep your money like you had when you were born, they started a savings account for you, and they knew that you weren't going to touch the money till you went to college, then sequence C would be the best place to have your money. And you'll notice that an exponential graph starts off really slow, but after a long period of time, it's going to be the fastest growing graph that we have. It's going to overtake linear, and it's going to overtake a quadratic over a long period of time. Okay, well, that's our lesson today, and I'm in your review preview, and there's some homework problems, and so I would like to work a few of those just to make sure you guys are on the right track. So here's some practice problems. So just take out a piece of paper, and you might jot these down, so when you do your homework, you'll have some good examples. All right, are the following sequences linear, exponential, or other? If linear or exponential, identify the rate of change and whether it is a constant that is added or multiplied. So we want to know if this is linear, exponential, or other. So let's look for a pattern. We are adding 4. We are adding 4. We are adding 4. So what type of sequence is this? This is a linear sequence because I'm adding 4. My sequence generator is plus 4. That is my constant that I'm adding every time. Okay, number 2, here's another sequence. Let's see if we can find a pattern. I'm increasing by 5. Here I'm increasing by 12. Here I'm increasing by 20. So obviously I don't have a constant sequence generator here. At least with adding. Now, if I try to multiply, I can't multiply 5 and get 17 and multiply the same thing and get 37 and multiply by the same thing and get 65. So it's definitely not exponential. So this is other. And there is no constant. Number 3, if I go from 5 to 20, it's definitely not the same distance as 20 to 80. So let's look at multiplication. 5 times 4 is 20. 20 times 4 is 80, and 80 times 4 is 320. So, since I am multiplying by a constant, this is exponential, and my sequence generator is multiplying by 4 every time. Okay, so that's how you would do the first few homework problems. And the next set of homework problems, it says to write the first 5 terms of each sequence. And this is written in recursive notation. So remember, this means term 1 is -2. So if it said to write the first 5 terms of each sequence, my first term is -2. To find the next term, and that's what this means right here. This is the term after the term that we know. To find the next term, what are we going to do? we're going to take that first term, which is t of 1, and we are going to multiply by 4. So what's negative 2 times negative 4? That would be positive 8. Notice that my sign changed because I'm multiplying by negative. To find the next term, I'm going to take the 8 and I'm going to plug it back in here. 8 times negative 4 is negative 32. Negative 32 times negative 4 is 28. And 128 times negative 4 is negative 512. So there are the first 5 terms of my sequence. Last one. My first term is 6. This says take 6 and subtract 5. So I get 1. Then it says take that term, subtract 5 again, and you get negative 4. Take negative 4, subtract that term, and you get negative 9. Negative 9, subtract 5, you get negative 14. There are the first 5 terms in that sequence. Well, I hope those examples help you get started on your homework, and that is all for today.